The pendulum seems to demonstrate simple harmonic motion. In previous sections, you worked your way through simple harmonic motion and the mass spring system. Can you answer this question? What is it about the restoring force that defines a harmonic motion? A. The force is constant and dependent on the mass in this case. B. The force is always in the same direction. C. The force is proportional to the distance from the rest point. D. The force is aimed toward the rest point. Correct, but there is another correct choice. Correct. Simple harmonic motion occurs when the restoring force is always directed toward the equilibrium position and is proportional to the distance from the equilibrium position. This is expressed in Hooke's law, F equals minus kx. Our next step is to prove that this swinging pendulum exhibits harmonic motion. Consider the force that returns it to the rest position. Is the force proportional to the distance from the equilibrium position? Let's calculate S, the displacement of the mass along the arc. It is equal to the length of the pendulum L times the angle theta expressed in radians. Recall Hooke's law, F equals minus k times x. Since the displacement of the pendulum is S equals L times theta, and L is constant, the restoring force should be proportional to the angle theta for the pendulum to exhibit harmonic motion. Take a minute to analyze this sketch. The forces acting on the mass are the gravitational force mg and the tension T exerted by the string. The gravitational force can be resolved into a component along the string, mg cosine theta, which is opposite to the string's tension, and a component perpendicular to the string, mg sine theta, that is tangential to the mass's displacement and is always directed toward the equilibrium position. Only the tangential force, F equals minus mg sine theta, is a restoring force. Since m and g are constant, they can be combined and replaced by the single constant k. Accordingly, F equals minus k times sine theta. The restoring force is not proportional to minus k times theta, but to minus k times sine theta. The restoring force does not satisfy Hooke's law. Therefore, the pendulum does not exhibit harmonic motion. But wait, there is a special case where a pendulum's motion is very close to being harmonic. When the angle is less than 15 degrees or 0.26 radians, the sine of the angle is roughly equal to the angle itself. This means that the restoring force F is approximately equal to minus mg theta. Since the displacement S equals L times theta, the restoring force can be written as F is equal to minus mg over L times S. Because m, g, and L are all constant, this expression has the form of Hooke's law, F equals minus k times the displacement x. Therefore, when the angle is less than 15 degrees, or 0.26 radians, the swinging pendulum exhibits simple harmonic motion. Using the fact that 180 degrees equals pi radian seconds, how many radians equals 12 degrees? A. 67 radians. B. 0.067 radians. C. 3.14 radians. Correct. Try this question. How many radians make up 8 degrees? What is the value of sine of this angle? Correct. 8.0 degrees equals 0.044 radians, and the sine of 0.044 radians is 0.044. So, we can conclude that the sine of a small angle is equal to that angle. Just remember to use radians. If we recall that the period t of the simple harmonic motion of a mass string system is equal to 2 pi times square root of m over k, we can determine the period of the pendulum. Since the restoring force, exerted by the gravitational force on the pendulum, is analogous to the force exerted by the spring on the mass for the displacement s, we can write that minus mg over L times s is equal to minus k times s. We obtain mg over L equals k, or m over k equals L over g. Substituting L over g for m over k in the expression for the period of the mass spring system, we find that in the limit of a small displacement, the period of the pendulum is equal to 2 pi times the square root of L over g. Since the frequency is the inverse of the period, we obtain that the frequency of the pendulum is equal to 1 over 2 pi times the square root of g over L. It is interesting to note that the only factor that affects the period or the time of the swing is the length of the string, not the mass. And assuming a small angle of displacement, there is no dependence on the amplitude, just the string length. A pendulum of length 0.50 meters, mass 1.0 kilogram, and displacement angle 12 degrees has a period of 1.4 seconds. If the mass is doubled, what will the period be? Correct. The only factor that affects the period, or the time of the swing, is the length of the string, not the mass. What's the period of a clock pendulum that is 0.75 meters in length? Correct. Check the form of the solution. It is important that you show all of the steps when you work problems. If a pendulum clock runs fast, how should the length of the pendulum be adjusted to correct the problem? Correct. You must have noticed that the period is proportional to the square root of the pendulum length. Did you know that the value of g is different in different parts of the world? Even if we maintain the same distance from the center of the Earth, the varying densities of the different materials that lie between us and the center of the Earth will result in different values of g. Geologists use a device containing a pendulum of known length and period to measure g at different locations. Suppose that a pendulum of length 0.50 meters has a period of 1.2 seconds. What is the value of g? Incorrect. Correct. Hopefully you showed all the work and used the correct number of significant figures.